Bismillah ar-Rahman ar-Rahim. I am Dr. Jamil uh, from the Physiology Department, and this lecture is in continuation with the lectures of the renal physiology. And we have concluded up to we have started the acid-base balance, and then we have covered the different types of the buffers, mainly the bicarb buffers. We have seen the different functions of the kidney. Now we are moving onward. Today we are going to discuss the reabsorption of the bicarbonate. Basically, the kidney function is to reabsorb all the bicarb. This is the primary function of the kidney, is to reabsorb all the bicarbs. Why do we need to preserve the bicarb? Why do we need to reabsorb all the bicarb? Because bicarbs, they are utilized for the to balance with the hydrogen ion. To nullify the effect of the acid, we need the base. And we are going to study both the things simultaneously. On one side, we are studying bicarb reabsorption. On the other side, we are going to study the hydrogen ion secretion. So we are going to study both these things simultaneously. Now, the primary function of the kidney is to reabsorb all the bicarbs. Now these kidneys, they can excrete the hydrogen ion as it is, but it's a very small amount. And these kidneys, they can produce the new bicarbs also. Whenever we need extra bicarb to nullify the effect of the acid, whenever there is acidosis, whenever there is excess of the hydrogen ion in the body, we need to preserve not only the presence of the bicarb which are already present in our body. We don't want to remove them in the urine. We want to reabsorb them. We want to preserve them. At the same time, we can produce, our kidneys can produce extra bicarb to nullify the effect of excess of the hydrogen ion present in the case of acidosis. So, what is meant by the reabsorption, or how the bicarb is reabsorbed in our body? Let's see this diagram. You can see that there is a diagram, and in this diagram you will see that approximately 4320 milliequivalent of the bicarb is filtered out. Then you can see the filtered out over here. Then from here the filtered out, 85% is reabsorbed in the PCT. And this loop of Henle is not utilized, this lower portion is not utilized in the acid-base balance, while 10% is reabsorbed in the thick ascending limb of the loop of Henle, and approximately 5% is reabsorbed, approximately 4.9 or 5% reabsorbed in the distal convoluted tubule plus collecting duct, and only 1 mg is going to be excreted in the urine per day. This is a rough idea. Now let's see what happens in the proximal convoluted tubule and how the bicarb is reabsorbed in the proximal convoluted tubule. Now let's see this diagram. Here is the diagram for you, that this is the previous one. Now normally your GFR is 180 liter per day, and your normal value of the bicarb in the body is 24 milliequivalent. Here, if you multiply this, then you will get the result. You have got 4320 milliequivalent. Here is this one, and here is the present. This is the present in your filtrate per day. Now we eat extra hydrogen. We take extra hydrogen in our diet, and that is mainly through the different types of the acids or proteins. And this is 80 milliequivalent extra. If we add this 80 milliequivalent extra in this one, so approximately 4400 milliequivalent is. That means hydrogen ion secretion is, actually there is a titration. Titration means to absorb one bicarb, we need one hydrogen to be secreted out. And we are performing two beneficial functions for the body at the same time. On one side we are going to reabsorb the bicarb, at the same time we are going to get rid of the hydrogen ion, and there is a titration. that one hydrogen ion, when it will going to be secreted, it will be out from the nephron. Then at the same time, it is going to assist in the formation. It is going to assist in the formation of, sorry, reabsorption of the one bicarb. हेलो जी, हम बात कर रहे थे, वी आर डिस्कसिंग अबाउट द reabsorption of the bicarb. At the same time, there will be a secretion of the hydrogen ion, and we are studying these two things simultaneously. Let's see what happens in the proximal convoluted tubule, because reabsorption, the PCT is quite different than the reabsorption of distal convoluted tubule. Now, let's see the things in the detail. In the proximal convoluted tubule, you will see that here is the tubular lumen, where the urine is coming down. Here the tubular cells, and there is a peritubular capillary network where there will be the final reabsorption of things is going to happen. These are pinkish lines. These are peritubular capillary network, and this is your tubular cell, and this is the lumen. Now the bicarb, we are going to see how the bicarb is reabsorbed in the proximal convoluted tubule. So before discussing these things, keep in mind that this wall or the luminal surface of the tubular cells in the PCT, they are not permeable to this bicarb. So the bicarb cannot enter directly from here to here. For this, God has provided a very important thing. Allah has given a very important thing. Here you see that there is a hydrogen and the sodium counter transport. Sodium is going to be enter into the cell, and against which hydrogen is coming out. This hydrogen, which is secreted out from here, is going to combine with this bicarb, and they are going to form this carbonic acid. Then this carbonic acid is dissociated again into the water and the carbon dioxide. This carbon dioxide is going to be reabsorbed from here, and inside they combine together, and again there is a formation of the carbonic acid, and this carbonic acid is dissociated again into the bicarb and the hydrogen ion, and this bicarb is reabsorbed. Now this hydrogen ion, which is secreted out here, this hydrogen ion is not excreted in the urine. You will not see anything hydrogen down. So the hydrogen which is coming out over here, it is not going to cause the real acidification of the urine. That means there is no addition of hydrogen ion in the PCT. Hydrogen ion do come out, but this hydrogen ion assists in the reabsorption of this bicarbonate, and this bicarb is reabsorbed and again is dissociated into this one, and bicarb is reabsorbed. So in the proximal convoluted tubule, the reabsorption of the bicarb is sodium dependent. It is sodium dependent because sodium moves in and hydrogen will move out, and this hydrogen will combine with this one, and it is secondary active. And there is no role in the real acidification of the urine, because this hydrogen which do come out in the tubular lumen, it is not excreted in the urine. So when it is not excreted in the urine, so there is not real acidification of the urine. And third one, very important, that the bicarb which is reabsorbed over here, it is the same bicarb which is present over here. So this bicarb is known as an old bicarb. This is an old bicarb because this bicarb which is reabsorbed over here is the same bicarb which is present over here. That's why we will call it as an old bicarb. Actually, this hydrogen ion, whenever it comes out, its first priority is to combine with the bicarb. Whenever this hydrogen ion will combine with the bicarb, it will try to reabsorb this bicarb. When these bicarbs they are finished, then this hydrogen ion may combine something else like phosphate buffers. It may combine with the ammonia buffer, and whenever this hydrogen ion we will see very soon that whenever this hydrogen ion combines with other than bicarb, it will be excreted in the urine, and that will be known as the real acidification of the urine. Now here you can say just a comparison what I am saying now, that here in the PCT you will see that hydrogen ion is coming out against counter transport with the sodium. Hydrogen is going to combine with the same process I have told you earlier, and this bicarb is reabsorbed, and this is known as the old bicarb. But in the next you will see in the distal convoluted tubule, hydrogen ion is not coming against the sodium, because here we have got the hydrogen ATPase pump. We will see actually there are two types of the hydrogen ATPase pump. One is the alpha, other is known as the beta, or type A and type 2. I will discuss all these things very soon. So here you have got the hydrogen ATPase pump. The hydrogen is coming out, and this hydrogen, instead of combining with the bicarb, it is going to combine monohydrogen phosphate, and they are going to form the dihydrogen phosphate, and this dihydrogen phosphate is going to be excreted in the urine. But inside that cell, the process of the carbon dioxide combined with the water in the presence of carbonic anhydrase, carbonic acid, dissociation, ultimately this bicarb is formed, and this bicarb is reabsorbed over here. Now this bicarb is known as the new bicarb. Why it is new? Because here you will see in the lumen there is no bicarb. There is no bicarb. Here there is already a bicarb. This bicarb which is already present is known as the old bicarb. But here there is no bicarb. When there is no bicarb, but still we have got a bicarb over here. So this bicarb is the pure function of the kidney, is the pure production by the kidney. So this bicarb is known as the new bicarb. Now go back to the original things. So in the proximal convoluted tubule, bicarb reabsorption is sodium dependent, it is secondary active, there is no real acidification of the urine, and the reabsorbed bicarb is the old one or the same which was filtered out. This was about the reabsorption of the bicarb in the proximal convoluted tubule, and at the same time we have seen that the reabsorption of the bicarb in the distal convoluted tubule, but there is a bit detail of this phosphate buffer. Phosphate, and we will soon see the not only the phosphate buffer but also the ammonia buffer also. Here is the same diagram, the reabsorption of the bicarb. This is again the same thing, the reabsorption of the bicarb. Now let's see something about the other buffers, which is known as very important buffer, is the phosphate buffers. The phosphate buffers, they become very important in the distal convoluted tubule. Why they become important in the distal convoluted tubule? Because by the time the filtrate reaches to the distal convoluted tubule, most of it has been most of the water and the other things, they have been reabsorbed. Wait a minute, this is the actual slide for the phosphate buffer. It is known that titratable acid because you can measure it how much acid has been excreted. Its pK is 6.8 and it is going to produce a new bicarb. As I have told you, whenever the hydrogen ion is going to combine other than the bicarb, then it will assist in the production. It will be excreted in the urine, but at the same time that bicarb production will be known as a new bicarb. So the phosphate buffer is composed of monohydrogen phosphate and the dihydrogen phosphate. 75% of the filtered monohydrogen phosphate is reabsorbed in the proximal convoluted tubule, while the 25% is left for the buffering, and 25% become more concentrated by the time it reaches the DCT, distal convoluted tubule. Why it become more concentrated? Due to the reabsorption of the water. Now this buffer, phosphate buffer, is a very good buffer in the distal convoluted tubule and collecting ducts, because when the filtrate enter in the nephron, its pH is same as that of 7.4. When filtrate enters, pH is same as that of plasma. But as the filtrate travels down to the nephron, its pH is going to be decreased or reduced due to the addition of the hydrogen ion. and by the time it reaches to the distal convoluted tubule, due to the addition of the hydrogen ion, the its pK, the pK which is 6.8, so the pH of the filtrate becomes very near to the pK of the buffers. And I have told you in my previous lectures, whenever the pH and the pK they become close to each other, the buffering power will show its best performance. So by the time this filtrate reaches distal convoluted tubule, its concentration become more due to the reabsorption of the water, and its pH of the filtrate become near to the pK of the buffering, this phosphate buffer. That's why this buffer gives its best performance in the distal convoluted tubule and the collecting ducts. Now here your phosphate buffers, you will see that if the hydrogen ion is coming out, the sodium is going to reabsorb and counter transport hydrogen, and this hydrogen ion is going to combine sodium monohydrogen phosphate. They will form the sodium dihydrogen phosphate, and it will be excreted. So here hydrogen is not combined with the bicarb. Hydrogen is not combined, it is going to combine with the phosphate. But at the same time you will see the other side. There is a continuous production of the combination of carbon dioxide, water, carbonic acid, bicarb and hydrogen. This bicarb is going to be reabsorbed, and this bicarb is known as a new bicarb, because here you will see there is no bicarb. On this side in the lumen there is no bicarb, but here you will see a bicarb. This bicarb is known as a new bicarb. Now keep in mind that the phosphate buffer, they will produce new bicarb. At the same time, your ammonia buffers, they also produce new bicarb. And we will see soon the other things regarding this one. Now back to the ammonia buffer. This is all about the phosphate buffers. Now the important point for the phosphate buffer is that the phosphate buffer become important in the distal convoluted tubule and the collecting duct. Why it become important? Because its relative concentrations increase due to the reabsorption of the water. Second, due to the addition of the hydrogen ion, pK become very close to the pH of the filtrate in the distal convoluted tubule. That's why this big buffer gives its good performance. This was all about the bicarb buffer. Let's see the ammonia buffer. I used to say one very important thing, that the ammonia buffer, actually the friend in need is a friend indeed. This ammonia buffer. This ammonia buffer, whenever the patient is suffering from the acidosis, particularly the chronic acidosis, it is a real friend. This ammonia buffer will perform its function, and it will continue to perform its function until and unless patient become normal. So ammonia buffer, why it's become very good buffer, ammonia buffer, why it can continue, why it's a good friend? Because the raw material for the production of the ammonia is present in your body, and that is an amino acid known as the glutamine. This glutamine is permeable to the tubular cells. The glutamine, they are permeable, and glutamine, when it is going to metabolize, it will produce two bicarbs and at the same time two ammonium ions. So I have to use one word very good in Urdu, jak nashud do shud. So the glutamine is giving not only bicarb, which is the two bicarbs, and at the same time they are producing two ammonia. And ammonium, and these two ammonium, they can move out against the sodium, and in the lumen it is going to combine with the chloride. Ammonium chloride will be formed and it will be excreted in the urine. On the same time, you will see the same thing over here in this color diagram, that the glutamine enters and glutamine dissociate into the ammonium and the bicarb. All these things are going to occur. This very helpful in chronic acidosis, and ammonium excretion increases up to 500 milliequivalent. Its pK is 9.2. and it is composed of two very important things, ammonia and ammonium. Now this in the extracellular fluid, hydrogen ion stimulates the glutamine metabolism. The hydrogen ion when it becomes excess, there it will stimulate glutamine metabolism. Normally 50% of the acid excretion and new bicarb production is done by the ammonia buffer. So the 50% of the acid excretion, very important, 50% of the acid excretion and the new bicarb production is done by the ammonia buffers. Only 5% of hydrogen is secretion is through ammonia, but can be increased up to 900 fold. 900 times can be increased. So this ammonia buffer, I am again saying, is a very good friend in case of chronic acidosis. Why it is become 900? Because tight junctions which are really very tight. Actually the tight juncture you will see in this diagram. In the PCT, tight junctions are so called tight junctions. They are not actually very tight. And here you will see there is a real tight junctions. So this ammonia buffers, they are going to produce, they are going to help out the person suffering from the chronic acidosis. Now let's see another very important thing, that this excretion of the hydrogen ion, or you can say the ammonium, difference of the ammonia and the ammonium. There are two ways for the excretion of the ammonium. The one way is that ammonia gas is free to move out. It can move out very easily. It's highly permeable. So this ammonia can move out and hydrogen will come out through hydrogen ATPase pump, and in the lumen they are going to combine with the chloride and this ammonium chloride is going to be excreted. This is the one way. And other way, which I have told you earlier, that the glutamine it is going to metabolize, it form the two ammonium ions. These two ammonium ions, they will come out and they are going to combine with the chloride, that ammonium chloride is formed and it will be excreted from the body. So there is a two ways. One is ammonia gas free to move and the hydrogen ion combination occurs in the lumen, and other is the ammonium ion move out with the counter transport with the sodium as shown in the previous diagram, then it will form the sodium chloride. So this was about the ammonia buffers. So we have seen the hydrogen, so we have seen the bicarb buffer in the previous lecture. Now we have covered the ammonia buffer and the phosphate buffers. And this is a very important function of the kidney is to produce new bicarbs. So again, the primary function of the kidney is to reabsorb all the bicarb. Its function is to reabsorb the to produce the new bicarb, and the kidney can excrete the hydrogen ion as it is, but a very small amount.